Good morning students, welcome to CM3107 e-learning day. Today we will be covering lesson 7.6 structures of metal as well as lesson 7.7 amorphous solid. The objective of today's e-learning module is to account for the various physical properties of substances in terms of their structure and bonding. As we all know, the physical properties of chemical substances depends both on the arrangement of particles, where we look at the structure, as well as the attractive forces between the molecules, where we look at the chemical bonding. Substances can be classified into four basic structures, namely ionic structure, simple molecular structure, micromolecular structure, as well as metallic structure. First up, ionic structure. Ionic compounds are made of oppositely charged ions held together by strong electrostatic forces of attraction, otherwise known as your ionic bonds. They form a three-dimensional lattice. For example, your common salts such as your sodium chloride, magnesium oxides are examples of ionic compounds. As seen in the schematics, your oppositely charged ions are held together by ionic bonds to form a three-dimensional lattice. Moving on, simple molecular structure. Your simple molecular covalent compounds are made up of discrete covalent molecules held together by weak intermolecular forces, such as your London dispersion forces, dipole-dipole forces, as well as your hydrogen bonds. For example, we have solid water in the form of ice, which are held by your hydrogen bonds, argon, which are held by your London dispersion forces. Similarly, for your iodine, they are also held by your London dispersion forces. So as seen in this schematic, we have water molecules, which are held by hydrogen bonds to form ice. Next up will be our macromolecular structure, which are made up of atoms held together by strong covalent bonds. The two most common examples are your carbon and graphite, which are allotropes of carbon, having different arrangement of carbon atoms joined together by strong covalent bonds. Last but not least, let us discuss about metallic structure, which are metals are made up of positive ions held together by strong metallic bonds. For example, your metals like copper, aluminum typically have this lattice of positive ions surrounded by your sea of delocalized valence electrons. We shall discuss the first physical property of the following structures of metal. Your ionic compounds generally have very high melting and boiling point. For example, your sodium chloride will have a very high melting point of 801 degrees Celsius. As such, most of your ionic compounds are solid at room temperature. Other characteristic properties of ionic compounds is that they are hard and brittle. A simple molecular structure, on the other hand, have relatively low melting and boiling point. Usually, their melting and boiling point range below 200 degrees Celsius. As a result, your simple molecular structures or simple molecular covalent compounds are usually liquid or gases at room temperature. Moving on to macromolecular structures, they usually have very high melting and boiling point. This is because of the strong covalent bonds that holds atoms together. As such, the physical state at room temperature will be solid. Other characteristic properties of macromolecular structures we will be discussing about graphite and diamond. Diamond is hard and rigid, whereas graphite is soft and slippery. We will be discussing on the structure in the effect of structure on the properties. Last but not least, let us discuss about metallic structure. Metals usually have very high melting and boiling point. For example, titanium, which has a melting point of 1668 degrees Celsius. As such, most of your metals are solid at room temperature, with the exception of mercury. Other characteristic properties of metals are that they are malleable and ductile. Your ionic compounds, macromolecular compounds, and your metals have high melting point and boiling point because a lot of energy is required to overcome the strong bonds between the particles in their respective structures. Consequently, at room temperature, there is insufficient energy to overcome these bonds, and therefore your compounds as well as your metal exist as solid. On the other hand, simple molecular covalent compounds are usually liquid or gases at room temperature. This is because of the weak intermolecular forces between the molecules, resulting in the low melting and boiling point. So let's take a look at example through hydrogen chloride. In your hydrogen chloride, your hydrogen atom covalently bonded to a chlorine atom in a hydrogen chloride molecule. These covalent bonds are strong. However, as we all know, hydrogen chloride exists as a gas at room temperature. This can be attributed to the weak intermolecular forces that exist between your hydrogen chloride molecules. So, it is important to note that physical processes such as melting or boiling involve the overcoming of intermolecular forces of attraction and not the breaking of covalent bonds within the molecule. Let us now discuss about other characteristic properties of ionic structures. Ionic compounds, as we all know, they are hard and brittle. Why so? This is because when we have force being applied to an ionic solid, what it does is that it shifts the layer of the ions slightly, such that ions of the same charge are now brought side by side and results in repulsion between the layers. The repulsion between the layers causes the crystal to cleave, giving rise to smooth and flat surfaces when the crystal is cleaved. So over here I have an example of sodium chloride. A crystal of sodium chloride, when I apply a force on a crystal of sodium chloride, what happens is that it's going to break. But take a look at how it breaks. Look at the sample on the far left bottom corner. You realize that it cuts to give a very clean, smooth and flat edge. On a microscopic level, what is being observed is that in a crystal lattice of sodium chloride, in this model, sodium ions are being represented by the yellow sphere, whereas your chloride ions are being represented as the pink spheres. When a force is being applied on a crystal lattice as such, what you have is that there's a slight shift in the layers of ions, causing like ions to be side by side. For example, you can see the sodium ions are now side by side together with the chloride ions being side by side. It causes its repulsion between these two layers that cleaves the ionic crystal into halves. Other characteristic properties of your macromolecular structure is that your graphite being layered has weak interlayer forces between the layers, making it a very soft and greasy substance because these weak interlayer forces allow these layers to readily slide past each other when rubbed. Diamond, on the other hand, is hard and rigid because your carbon atoms are now being held in a continuous and tetrahedral arrangement of atoms via strong covalent bonds. Note that graphite and diamonds are allotropes of carbon. Allotropes are different structural forms of the same element. Because of the different structural form, allotropes can exhibit quite different physical properties as well as chemical behaviors. Other characteristic properties of metallic structure is that metals are often described as being malleable and ductile. Why is that so? This is because your metal atoms, or rather the layers of metal atoms, are able to slide over each other into new position without breaking the metallic bonds. As shown in this schematic over here, when I apply a large force, layers of metal atom are able to slide past another layer of metal atom without breaking any bonds. So therefore, based on that, we expect metals to be structurally soft. Typically, the hardness of metal is improved by forming alloys. To form alloys, atoms of other sizes are being introduced in the metal lattice. This is to prevent layers from sliding past each other, therefore giving improved properties of hardness and strength to the alloy. So over in this schematic, a substitution atom highlighted in blue is being introduced into the metal lattice. The different size of this substitutional atom prevents layers of the metal atom in red from sliding past each other, therefore giving the alloy the improved properties of hardness and strength.